in our previous lecture we have defined the convergence of iterative methods. We have also obtained the optimal relaxation factor for the SOR method, and if we can determine this value of the optimal relaxation factor accurately, then the amount of computational cost reduced or the saving that we have made would be enormous, almost to the order of factor of 10 or could be more also in a particular problem of a big system. Now, let us take a simple example of how we are going to determine this optimal relaxation factor for a given method. So, let us take this as an example. So, we will say find the optimal value of the relaxation factor in the SOR method for solving. We will give a simple system of equations for solving the system of equations 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2 x 1 x 2 x 3 is equal to 7 1 1. Find also the rate of convergence. Now, we have given two formulas for the finding the optimal value and the rate of convergence for the SOR method, and we have given the formula that the value of the relaxation factor which is optimum is given as 2 upon 1 plus under root of 1 minus mu square, where mu is the spectral radius of the iteration matrix of Gauss-Jacobi scheme. Therefore, I would write down the iteration matrix for the Gauss-Jacobi scheme, find its spectral radius, use that and find the omega optimal. When once I find the omega optimum, then I can write down the spectral radius of the SOR scheme as omega optimum minus 1. Then I can define the rate of convergence of this as minus log of, therefore, I will have the rate of convergence of SOR scheme, or we can just simply rate of convergence of SOR scheme is minus log base 10 of spectral radius of HSOR. Therefore, I need to find these three quantities to complete this particular problem. Now, let us first of all write down what is the iteration matrix for the Gauss-Jacobi scheme. So, let me just keep it as it is. Now, for the Gauss-Jacobi scheme, we have minus d inverse of L plus u . Now, the diagonal matrix is 2 2 2, therefore, I can invert it immediately as 1 by 2 1 by 2 1 by 2. So, I will have here 1 by 2 0 0 0 1 by 2 0 0 0 1 by 2. Then L plus u is the remaining part in the matrix, therefore, what is left out would I will write 0 minus 1 0 minus 1 0 0 0 minus 1 0. So, the diagonal has been picked out already. So, what is left out is L plus u, the remaining elements. Let us multiply it out. This gives us, this is 0 minus half 0. No, there is a minus 1 here, there is a minus 1 here, there is a minus 1. Therefore, I will have a minus half here, 0 minus half here, 0 minus half 0. Now I will find the eigenvalues of this. So let us just find out, let us drop the suffix and simply write h minus lambda I determinant. Therefore, let us absorb this minus sign inside. So all these are positive quantities and I am subtracting minus lambda I. Therefore, I will have minus lambda plus half 0 plus half minus lambda plus half 0 plus half 0. This determinant is equal to 0. Now let us apply the simple formula. Let us write down the expansion of this determinant. This gives you minus lambda that is lambda squared minus 1 by 4. This is minus half and we are multiplying these two. So, we will have lambda by 2 is equal to 0. And I can minus lambda I can take out common factor. So, I have lambda squared minus 1 by 4 minus 1 by 4. I have taken minus sign out. So, I will have left out with a minus 1 by 4 again. Therefore, I will have the values as lambda is 0, lambda square is 1 by 4, that lambda is equal to plus minus 1 by 2. Oh yes, let us write it here. Okay. Lambda square is equal to 1 by 2, lambda is equal to, let us write down all the 3 roots, lambda plus minus 1 upon root 2. Therefore, I can write down the spectral radius of this Gauss-Jacobi as 1 upon root 2. Now, I would substitute this in the value of omega optimum. This is our, therefore, omega optimum will be 2 divided by 1 plus under root of 1 minus mu square. This is our mu, this is our mu. Therefore, this is 1 upon 2. So, let us take this 2 up. So, I will have here 2 times root 2. This is 1 plus root 2. This is 1 and this is your root 2, and this is approximately 1.1716. I have rounded it off to the next digit. So, this last digit I have rounded to the next figure. Therefore, now I will have the spectral radius of HSOR is omega optimum minus 1. So, I will have simply 0.1716 as the spectral radius of the SOR matrix. Hence, I will have the rate of SOR method is equal to minus log base 10 1716, which is the value is 0.7656. Now, you could just try to compare right here as to how do we compare SOR with Gauss-Jacobi itself. If I look at this, we have written here the spectral radius of the Gauss-Jacobi is 1 upon root 2, that is approximately 0.7. This is 1.414, ratio is about approximately 0.7. Therefore, in place of 0.7 we shall use 0.1716 here. This gives us the value of the rate of convergence 0.7656. The rate of convergence of Gauss-Jacobi is much lower, because this we are having minus log 10 approximately 0.7 is what we have get here for the rate of convergence of the Gauss-Jacobi, and which is a much smaller quantity than this. As we approach 0, the log of 0 goes to infinity minus infinity. So, as we approach 0, it is going to be bigger and bigger. So, this is a bigger number. So, we will have the rate of convergence is a much smaller number. Therefore, you can see the convergence rate here itself, such a huge difference in the convergence rate. Therefore, in this particular problem will converge, SOR will converge very, very fast compared to the Gauss-Jacobi scheme. Okay. Now let us go to the other problem we mentioned about the eigenvalue problems. So let us discuss about the eigenvalue problems. Eigenvalue problems is also a very important problem in the areas of mechanical engineering, civil engineering and many other areas also. It does occur very often. Now we have given brief introduction what the eigenvalue is. Let us just remember what we have done there and little bit more so that we can use that for finding the numerical methods. So the basic problem is that we have Ax is equal to lambda x, we have Ax is equal to lambda x, lambda is a real or a complex number, lambda is a real or complex number. Then we have defined the characteristic equation as the determinant of A minus lambda I. If I expand this, it is a polynomial in lambda of degree whatever the degree of A. So this is a polynomial in lambda of degree n. We have taken A as a n into n matrix. Therefore, we get a polynomial of degree n in lambda. The roots of this equation are the eigenvalues which may be real or complex. But we know the property that if lambda I is an eigenvalue of A, if lambda I is an eigenvalue of A, then A square will have eigenvalues lambda I square, A to the power of m will have eigenvalues lambda I to the power of m. So the mth power of this is an eigenvalue of A to the power of m. Let us assume that A is non-singular, that means the determinant of A is not equal to 0, then 1 upon lambda I is an eigenvalue of A inverse. Now what is also important to know is about the property of the eigenvector. Let us just look at these last two properties and see what will be the eigenvector. If I start with Ax is equal to lambda x, I pre-multiply by A. So this will be A squared x is equal to lambda into Ax, lambda is a number, so I can take it out. So this will be lambda square x. It is from this that we have concluded that lambda square is an eigenvalue of A square. So if I continue on, I get A to the power of mx is lambda to the power of mx. Therefore the eigenvector is the same, the eigenvalue is lambda I to the power of m will be the eigenvalue of A to the power of m, but the eigenvector is the same. Therefore this is important for us to know that the eigenvector is same, the eigenvector does not change. I want to find the property for the inverse. So I again start with Ax is equal to lambda x, pre-multiply by A inverse. So I will have lambda into A inverse of x, then I bring lambda here in the denominator. So I will have here A inverse of x is equal to 1 upon lambda of x. I have written the right hand side first, this is 1 upon lambda of x. Therefore this is showing that 1 upon lambda is the eigenvalue of A inverse and x is again the same. Therefore the eigenvector in this case is also same, eigenvector is same. Another important concept which you have done earlier is a similarity transformation. Let us define what is a similarity transformation. Similarity transformation. I take any non-singular matrix S, S is a non-singular matrix. Then I form the matrix B is S inverse A S, S inverse A S. Then I define this as a similarity transformation. This is called a similarity transformation. Similarity transformation. Now, we also say that A and B are equivalent matrices. In this case, sometimes we say that A and B are equivalent matrices. Now, in what sense they are equivalent is that we can show from the property of the eigenvalues that A and B have the same eigenvalues. This actually implies that A and B has the same eigenvalues, have the same eigenvalues. The eigenvectors are different, but the eigenvalues are the same eigenvalues. Therefore, the importance of this particular property is that given a matrix A, if I can use a particular non-singular matrix to reduce A to simpler form, then I can find the eigenvalues of the new matrix easily, and hence they are the same eigenvalues of the original matrix. Therefore, I can find the eigenvalues of the original matrix. This is the basic concept that we shall use in all the numerical methods for the eigenvalue problems. Now, the second property in this is we picked up S is any non-singular matrix. Let us suppose that S is the matrix of eigenvectors. Let us suppose it is a matrix of eigenvectors. Let us put some S1, S2 vectors, these are vectors S1, S2, Sn. These are column vectors, S1 is a column vector, S2 is the second column vector, Sn is the nth column vector. So, this is the matrix of eigenvectors. Then S inverse AS would always reduce to a diagonal matrix. It will be a diagonal matrix, and the eigenvalues are placed on this. This result is obvious from us because we just made a statement that if A and B are equivalent, A and B have the same eigenvalues. Now, S inverse AS has been reduced to a diagonal matrix, and hence the eigenvalues of A and D are same, and the eigenvalues of D are simply the diagonal elements itself. Therefore, lambda 1, lambda 2, lambda n which itself will be the eigenvalues of this particular matrix. Furthermore, in this case there is 1-to-1 correspondence between the position of this column and the eigenvalue. What I mean is that S1 here is the eigenvector corresponding to lambda 1, S2 is the eigenvector corresponding to lambda 2, Sn is the eigenvector corresponding to lambda n. That means, in this position there is 1-to-1 correspondence between the columns of S and the eigenvalues located on the diagonal. So, there is 1-to-1 correspondence between the columns of S and the location of eigenvalues on the diagonal of D, on the diagonal of D. The method that we are going to describe just a little later would concentrate on reducing a given matrix A to this diagonal form. Hence, I have the eigenvalues of this particular problem, and there automatically I have the eigenvectors located as columns of this matrix that I am producing it over here. Therefore, I have both the eigenvalues and the eigenvectors in one particular step itself, and I can give both of them. Now, in many applications you may not really require all the eigenvalues. For a particular application you need to know what is the largest eigenvalue that this system has got it, or you want to have simply a bound of the eigenvalue and not really the eigenvalues, because to get a bound of an eigenvalue is much more simpler problem than actually finding the eigenvalues. So, let us find how we can get some bounds for the eigenvalues. Now, one bound which we already done earlier while describing norm. If you remember, we have shown that norm of A is always greater than spectral radius of A. This property we have proved. I will rewrite it as spectral radius of A is less than or equal to norm of A. Now, the definition of spectral radius of A is it is the largest eigenvalue in magnitude. Therefore, the left hand side is magnitude of lambda I. So, all eigenvalues satisfy. Therefore, the left hand side would imply that magnitude of lambda I is less than or equal to, we use any norm that we know here, that is the maximum absolute row sum. Let us take this as maximum absolute row sum, that is maximum with respect to I of summation of all the elements in the row, that is this is this. This we have called it as maximum absolute row sum. We call this as maximum absolute row sum. So, this is a bound for our eigenvalue, and I will use this as second one. I will take the maximum absolute column sum as my second bound. Magnitude of lambda I is less than or equal to maximum with respect to j, I is 1 to n a I j. So, this will give us maximum with respect to j, this is the maximum absolute column sum. Now, these are the two obvious bounds that we get from here, but these are very rough bounds, but we would now like to get which are some more sharper than these ones, and for this we would like to look at our basic problem Ax is equal to lambda x. Let us pick one eigenvalue, lambda I is an eigenvalue. Let us take a particular eigenvalue and let us take the corresponding eigenvector. This is the corresponding eigenvector. That means, we are talking of A x I is equal to lambda I x I. Now, I need the components of x I. So, let us write down x I, its components as x I 1, x I 2, so on x I n. So, let us write down the components of the vector x I as with the suffix as I 1, I 2, I 3, I n. So, that will be the components of the vector x I. Now, let us open up A x I into this one, therefore, A 1 1 into this plus A 1 2 into this and so on. So, let us write down this system A 1 1 x I 1, A I 2 x I 2, O 1 A 1 2, A 1 n x I n is equal to right hand side is lambda I x I 1. Right hand side is lambda I x I. So, lambda I multiplies this first one x I minus 1. So, I need the kth one A k 1 x I 1, A k 2 x I 2, A k n x I n, lambda I x k k n x I n, that is equal to lambda x k x I should have put here x I k, this is x I k, and the last element is x n 1 x I 1, A n 2 x I 2, A n n x I n, lambda I x I n. Now I will take a particular equation, arbitrarily any equation. Let me pick this equation as the kth equation. So this is my kth equation, this is my kth equation. I will take this as my kth equation. What I do here is, of all these components in this line xi1, xi2, xi3, xin, I will pick up that particular largest element in largest component in magnitude. So xik, a particular this one, I will take this as the largest element. That means what I am really doing here is, I am I have taken this xi, I find the largest element in magnitude in these components, and I find that xik is the largest element in magnitude. So I have found that xik is the largest element in magnitude of all these components. Now I will pick up that particular equation to tackle it and find the bound, and if that is xik is the largest element in magnitude, I will pick up the corresponding equation, that the kth equation that I have here. So if once I pick this equation which has the largest element in magnitude, what does this imply? The ratio of xi any j divided by xik in magnitude is going to be less than 1, because xik is the largest element in magnitude. If I take the ratio of the other components j not equal to k, then this is always going to be less than 1. That is the definition of our largest element in of xi. Now let us take from this xik, this element that is here, to the right hand side. This is your akk element, will go to the right hand side and combine with this one. So what I will have here is lambda I minus akk, lambda I minus akk, and let us retain our xik also for the moment. This is the, I have taken this element to the right hand side. Then I will write this in summation notation. This is the remaining elements of your this particular row, that is your akj, xij, j is 1 to n, j not equal to k. I have taken all the elements written here except the term corresponding to j not equal to k. Now I divide by this xik and then take the magnitude of it. So I can write down magnitude of lambda I, this is equal to summation of j is 1 to n Now when once if I take the magnitudes inside, I shall then insert less than or equal to this, that is equal to xij by xik. But these ratios, they are all strictly less than 1. Therefore this would imply that this is less than or equal to simply j is equal to 1 akj. Yes, modulus of akj, yes. If you just compare what we have taken, the absolute row sum of which one element has gone to the left hand side as combined with the lambda I, and these are the remaining elements here, and these are the sum of the magnitudes of these remaining elements. Now but however we do not know what is k, we have picked up, but in practice we do not know. Therefore what we do is we will take the union of all these inequalities. So k is unknown, k is unknown, therefore lambda lies in the union of the, at the moment let me write down inequalities, but we will later give another name to this inequalities lambda minus aii or akk, you can retain AKK less than or equal to j is 1 to n, j not equal to k, AKJ, k is 1, 2, 3, so on n. Therefore, there are n inequalities of this particular type and we will get n of them, and the union of all these will be the required bound. Now, this we will take as the third bound that we have done. Now, we know that the eigenvalues of A and A transpose are same. So, we know if I take the A and A transpose, for both of them the eigenvalues are same. Eigenvalues are same. Therefore, this inequality would simply become magnitude of lambda minus AKK is less than or equal to summation I is we are taking k here. So, let us retain k is equal to 1 to n magnitude AKJ, j not equal to k for all j. That means, we are forming the same thing with respect to the columns, and the union, the again lambda lies in the union of the n inequalities. Now, we have got here essentially 4 bounds. The 4 bounds are these: one is simply the maximum absolute row sum, this is maximum absolute column sum, then we have obtained this third bound as this, and this is a fourth bound, but all these bounds are independent bounds. Therefore, if each one of them is giving a particular bound and all of them are independent, the intersection of these bounds should be the final required bound. Therefore, the final bound will be intersection of these 4 bounds. This would give us a quite good estimate of this, but we know that the eigenvalues lambda, they are real or real and complex or real and complex. Now, if they are real and complex, that means let us take lambda is equal to x plus iy. Suppose they are complex, lambda is x plus iy. Then all these, the first 2 bounds are stating that magnitude of lambda is less than or equal to some constant c, some number which is a number. If it is complex, this would imply this is under root x squared plus y squared is less than or equal to c, or which implies x square plus y square is less than c square, which is a circle with center at 0 0 and radius c. Therefore, all the bounds that we have got here, at that time we have written it as inequalities. Now, we can show that all of them are circles. When once the eigenvalues becomes complex, they all become circles. Therefore, these are called the intersection of these n circles. Now, in place of these inequalities, I can now write down that these are n circles. Similarly, in the other case, and these are all called Gershgorin circles. They are called the Gershgorin circles. That means, we are talking of intersection of circles in the complex plane. You have got x and the real part is x, imaginary part is y. So, we go to the complex plane, and in the complex plane we can draw these circles, and from the circles we will find out what is the bounds of this for the complex eigenvalues also. But a particular case is when A is symmetric. When A is symmetric, the eigenvalues are no longer complex, they are all real. So, we know that eigenvalues are real. Therefore, these bounds would no longer be circles, it will be just simply intervals on the real line. Therefore, they will be intervals, the circles reduced to intervals on the real line. Now, let us just take an example on this, how we are going to find these Gershgorin circles. Let us take an example of this. Estimate the bounds of the eigenvalues of the matrix is 1 2 minus 1 1 1 1 1 3 minus 1 using Gershgorin bounds. See, an immediate application of this would be, let us suppose that in our iteration procedure of Jacobi or Gauss-Seidel or SOR, let us suppose the components of the coefficient matrix is 0.2, 0.5, 0.1, minus 0.2, minus 0.3, minus 0.3. Now, I can immediately, from using this, I can immediately find the spectral radius of it, because I know each eigenvalue would be lying within this circle. So, I can immediately say the norm of this is less than 1. So, I am guaranteed that this iteration is going to converge. I just do not have to do any other proof. I can straight away get the bound for the eigenvalue from the matrix itself, and then say our convergence is for the iterative procedure is guaranteed. So, that is the immediate application of this Gershgorin bounds. Let us write down all the 4 bounds. Magnitude of lambda is less than or equal to maximum of absolute row sum. Absolute row sum is 2 plus 3 plus 1 4, 1 plus 1 plus 1, that is 3, 1 plus 3 plus 1, that is 5. So, that is equal to 5. The second bound is magnitude of lambda is less than or equal to absolute column sum. This is 3, this is 6, this is 3, that is equal to 6. Now, you can see that these are all independent bounds, therefore, we can immediately throw this away, because magnitude of lambda, this is a circle with a smaller radius than this is a bigger radius, and we want finally the intersection. Therefore, this circle is not to be considered, because this is within this one. So, let us take the third one. What is important here is union of circles. Now, lambda minus a11, that is lambda minus 1, that is I am taking first element lambda minus a11 will be less than or equal to the absolute sum of the remaining, that is 2 plus 1 3. Lambda minus 1, I have taken the second pivot as 1 and the off diagonal elements as 1 and 1. So, I will have this as 2, and from the third row I get lambda plus 1 is less than or equal to 4. Now, before I proceed to the fourth one, we can look at whether any one of these bounds is contained in the other one. Now, let us just see that this is a circle with center at 1 radius 3, center at 1 radius 2. This circle is inside this circle. So, we do not need to consider this particular one, but these two are intersecting. So, we have to consider both of them. Now, the fourth bound is union of circles. Now, let us take with respect to column. So, the first column gives magnitude lambda minus 1 is less than or equal to 2. The second column gives us magnitude of lambda minus 1 is less than or equal to 3 plus 2, that is 5, and the third column gives lambda plus 1 is less than or equal to 2. This middle one, if you see this circle with center at 1 radius 5, this is center minus 1 radius 2, this is center 1 radius 2, both of them are contained in this one. So, these two bounds we need not even consider them because they are contained in this. Now, finally, we need intersection of all these 4. Now, this is a much larger circle, it is now this is the largest circle which we have excluded. Now, we finally have to write down the intersection of bound is the intersection of the first bound magnitude of lambda less than or equal to 5, that is the first bound that we have got from there. Then from the second union, this union of circles, magnitude lambda minus 1 less than or equal to 3, magnitude lambda plus 1 less than or equal to 4, and magnitude lambda plus 1 less than or equal to 2. Oh, sorry, this is magnitude of lambda minus 1 less than or equal to 5. I have taken this, picked up this one and this one. Now, it would be interesting for us to just look at how it is going to look like. Let us just draw a nice diagram. Let us try to draw a diagram of this one. Now, let us just make it very small, 1, 2, 3, 4, 5, 6 of them, 2, 3, 4, 5, 6. The first one is circle with center at the origin radius 5. So, I will have a so, this is our circle, that the first circle. Now, the second one is center at 1 radius 3, center is at 1 and radius is 3 of them. So, it goes through, this is the center, it goes through this and it goes to this, it goes through this. So, I will have a well, it is not very beautiful, it will be more accurate. Then I have circle with center at minus 1 0 radius 4. So, the center is at this and it passes through this and for this. So, I draw this diagram again. And finally, center at 1 radius 5. So, this is 6 and through this. So, this is a huge circle that comes like this. Now, I want intersection of all of them. So, what is common for all of them is only this. It should lie in all of them, all the independent bounds it should lie. We have to take the union of these two union of these two, this is a group. So, this group we have to take together, then intersection with this, union of these two and intersection with this. So, union of these two would give us the union of this and the other circle, and intersection with this final circle. So, this part will be excluded because this goes out in the intersection. So, this will be the bounds for the eigenvalues. So, you have to take the it is important is this is the union of these two. It is not the intersection of these 4, it is the intersection of this circle to the union of these circles and 3 this circle. Therefore, these are the 3 groups that we have, and the intersection of these 3 groups will be the required bound for the eigenvalue. So, this is how we can draw the location of the eigenvalues and then find out that the eigenvalues lie in this particular region. Now, let us take a simple example for a symmetric matrix. Let us take this example. Let me take this as 3 2 2 2 5 2 2 2 3. Now, this is a symmetric matrix. Therefore, eigenvalues are real. Eigenvalues are real. Therefore, it will be no longer be circles, it will be only intervals. Now, since it is symmetric, the bounds 1 and 2 will be the same, because absolute column sum will be same as absolute row sum. So, both of them would give you the same bound, that is magnitude of lambda is less than or equal to maximum of, that is equal to 7 9 7, that is equal to 9. And the third and fourth, both of them would again give the same one, that gives you union of the circles. These are not circles, these are now intervals. Now they become intervals, that is equal to magnitude lambda minus 3 is less than or equal to 4, lambda minus 5 less than or equal to 4, lambda minus 3 less than or equal to 4. Now, we can see that this is too big, therefore, the intersection we can throw away this particular bound, because this is much smaller than these bounds. Now, let us open it up. The first one, let us write it, this is minus 4 less than lambda minus 3 is less than or equal to 4. So, is an interval. So, let us open it up. This gives you minus 1 less than or equal to lambda less than or equal to 7. So, I have taken it to this side. The second one gives us lambda minus 5 less than or equal to 4, that is minus 4 less than or equal to lambda minus 5. Okay, let us write lambda minus 5 less than or equal to 4. I bring it to this side. So, I will have 1 less than or equal to lambda less than or equal to 9. Then I have the third one, lambda minus 3 less than or equal to 4 is same as the first one. So, this would also give you minus 1 less than lambda less than or equal to 7. Now, I need the union of these circles. I want the union of these two. The union would be, I want the union of this, that will be minus 1 less than or equal to lambda less than or equal to 9. Therefore, this is the bound for the eigenvalues of the system, and the exact eigenvalues of this, I will give you the values. This is 1, 2.17, 7.83. These are the exact eigenvalues of this particular 3 by 3 system, which you can see that we have got very good estimate of the eigenvalue. This is bound is 7.83 and we have got here as 9 as the interval. Now, you might have noticed one thing, that the 1 and 2 as indeed I have not given any bound in this one. Therefore, this is a very rough upper bound compared to these other union circles, that is Gershgorin circles. So, usually this is the bounds 3 and 4 are the best bound that will be available, the intersection of them would be the required bound. Okay, I will stop it.